I think you better prepare a question. If we for guys cannot understand your presentation, it will very interesting.
Let me see.
Question.
No, I don't have question.
One hour left.
Why we have to send?
Because probably borrow the key, they cannot help us this room. So maybe because of this right, we can borrow the key, but they said we must submit the key before 11:50. Okay, let's begin.
Good morning, everybody. My name is Thanh-Nam, and I come from Thanh-Nam National University. And it is my great pleasure to stand here and present to you my very recent research about hydrogen burn. And my topic for today is the origin of CH and hydrogen bonds in complexes of trihalomethanes and ammonia, with the perspective from energy decomposition analysis. As you may all know, the hydrogen bond is a very important non-covalent interaction among the scientists due to its ubiquitous occurrence and application in chemistry, biology, and also material science. And from the very beginning, hydrogen bond can be represented in the form of AHE, where H is more electronegative atom or group than hydrogen atom, and AH serves as the proton donor, where B is electron-rich atom or group and serves as a proton acceptor. And a very typical example of this type of bond is in the water molecules. And this type of bond is well known by its characteristics. The firstly is with strengthening the in AH bond length. Also, it causes redshifting, which means that it will decrease the AH stretching frequency, and also it will enhance the IR spectroscopy intensities. So that is the reason why this type of bond is called redshifting proper hydrogen bond, and the origin of the type has been well known by scientists, and there are two possible ways to explain the origin. The first one is based on electrostatic interaction, and the second one is based on charge and transport effect. But things become more complicated since 1980s, when scientists discovered a new type of hydrogen bond, which is have the characteristic totally opposite to the redshifting hydrogen bond, and it is called blue shifting hydrogen bond, with the characteristic is the shortening in AH bond length concomitant with blue shifting AH stretching frequency and a decrease in IR spectroscopy intensity. And this type of bond is very popular in some kind of biological molecule. For example, here the first one is in the high order structure of protein, and the second one is the helix structure of DNA. And among persisting hydrogen bond, the important interaction is Ca interact with oxygen atom, and Ca interact with nitrogen atom. And interestingly, these interactions belong to improper proton donor, CH, which is proposed by Demis and Joseph in an article in 2007. Which is improper proton donor. It means that the shifting of this type of bond depends strongly on the proton acceptor. It can cause blue shifting, or it can cause red shifting, depends on the molecule of O and N. And about the origin of blue shifting hydrogen bond, there are no general explanation. Many approaches have been proposed in order to interpret that type of bond. However, there are no agreement. I can categorize this approach into two mainstream lines. The first one is NPO-based approach, which scholars who belong to this approach stated that the origin is strongly based on the internal reorganization due to charge transfer or the rehybridization. The second way to approach is EDA-based approach, which is an energy decomposition analysis based approach. And scientists approach in this way try to interpret the origin of blue shifting hydrogen bond based on the repulsive wall, dispersion energy, and electrostatic energy, while the first one had been no longer reliable. The two remaining is still controversial. But very very recently in an article in Journal of Physical Chemistry, Starn, who is a professor in Cambridge University, has stated that MBO-based approaches are heavily contaminated with BSSE, and he stated that the symmetry adaptive education theory, which is SAPT method, were more reliable to investigate the weak interaction. So that is the reason why we choose this method to investigate the contribution of energy components in the formation of complexes. About the computational methods, we will firstly we will ab initio calculation, and all these calculations is conducted using Gaussian 09 package. With ZPE and harmonic frequency is calculated at a theory level of MP2311 plus C3DF2PD, and the SPE and BSSE were computed at a higher level as CC, SDT, and the same basis set. And the octane geometries were used to subsequently perform AIM, which is the RNA molecule, and an SAPT2 plus compilation. And after calculate the three complexes, we have found some interesting results. The first is the changes in CH bond length and its frequency. And you can see from three picture of three system, which is CHF3 with ammonia, CH3 with ammonia, and CHPR3 with ammonia. It can be seen that from a large distance, it is experiencing an increase in blowship, which is a contraction in CH bond length, and also an increase in the stretching frequency. And for the sake of comparison, we combine these three graphs into one, and we can see that there are differences in the chains of three system, which is CH3 tend to decrease more in the CH bond length, which is so that it prefers blue shifting than the other two. And also the distance where it turned into when it changed to increase the CH bond length, the CHF3 is later than the other two, which is about 2.9, while the other two are at 3.1 angstrom. So we can conclude that the redshifting tendency is preferred in the order of CF3 than CO3 and CHBr3. About the interaction energy, we also see the similar pattern in three systems where there are three systems experience redshifting at the equilibrium distance, but with different level, which is will increase from CH3 to CH3 and CHBr3. Again, we can conclude the preference in redshifting is increased in this order. But want to compare the order of interaction energy among these three systems, and as we can see, as this range, as a region, the interaction energy of CHL3 is lower than the other two, and from this distance when two molecules come closer, this type of energy increase more, which is indicating that CHL3 is more stable at larger distance, and at shorter distances, CHBr3 is more stable, and to CL3 and then CAL3. But we compare this result with SAPT outcome, and we can see that these two graphs are in very good agreement to each other. But for SAPT result, we can see that the order as longer distance where the intermolecular interactions are very weak, the order is more clear than in the ab initio calculation. So we can conclude, we can provide some conclusion. First, in region 1, which is as large distance, the stability increase in the order of CABR3, CL3, and CH3 because of electrostatic interaction. Into remaining regions, the order is reversed due to polarizability and SAPT results, so high accuracy for intermolecular interactions. So that's the reason why we would choose SAPT to further decompose the total interaction into smaller interaction forces. Now, we can see the correlation between electrostatic components and the changes in CH bond length. And we can see that in all three assembly systems, the electrostatic interactions is dominant and especially at far distance. So we could include that it will be the main force to stabilize the complex, and it can be. But when the electrostatic interaction dominant, it is supposed to have a redshift hydrogen bond. However, we can see that there are a trend in increase the blue shifting hydrogen bond, and we can explain based on the Jamie and Joseph idea, that is when the proton acceptor come close to the proton donor, at the electrostatic with the presence of the acceptor, the A atom and the hydrogen atom will interact more strongly, and cause a short rate interaction would keep the hydrogen close to A, and causing a red blue shifting hydrogen bond. But as you can see, as the distance come closer, the electrostatic interaction tends to decrease, while there is an increase in the blue shifting hydrogen bond. So we concluded that it does not control the shift of CH bond. And interestingly, we see a correlation between dispersal interaction and changes in CH bond length. As we can see here, this person increased as the CH bond length decrease, and we can see a very interesting correlation here. When the peak of dispersion is coincident with the change from the blue shifting to red shifting, so we can conclude that dispersions play a vital role in controlling the shift of CH bond length, and the higher percentage of dispersion interaction, the greater CH contraction, which is blue shift. So we come to some conclusion. First, all CAH3 NH3 systems demonstrate redshifting HBs at the equilibrium distance, but with different levels. The redshift tendency increases from CHF3 to CHCl3 to CHBr3. The stability of complexes increase in the order of CHF3 to CHCl3 to CHBr3 in region 1, and in reverse order in the other regions, confirmed by both ab initio and SATT2 plus calculation. And the last one, the most important, electrostatic interaction is the main component for the complex stability, but is not the key factor driving the shift of ABs. But the person interaction plays a vital role in controlling the shift of the hydrogen bonds. That's the end of my presentation, and thank you for your kind attention. If you have any questions, don't hesitate to ask me, and I will very happy to answer.
I have a question for you.
Yes.
So, does the results have any contaminations by the solvents of the examined complex?
Oh, it is a very interesting question. In computational chemistry, there are many different ways to compute. There are some methods which is based which is depends strongly on the solvent, but my calculation is calculated at the gas phase, so it do not require the solvent. So I believe that the solvent aerosol will be totally not contaminated by the solvent. Thank you.
Yes.